Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Bracketing Methods. Method of false position. The method of false position is also based on bracketing a root in a tight interval like the bisection method. It differs only in computing the new estimate. A straight line passing through the endpoints of the current interval is constructed. For the endpoints it yields, the root is approximated by finding the x-intercept as follows. Consider the function f, x, plotted in the interval a to b. We observe that the signs of the function values at the endpoints are opposite, that is, the function has a root in this interval. We then denote the interval endpoints with superscript 0 notation to indicate the initial values. Next, we connect the endpoints with a straight line, which intersects x-axis. Even though it is far from the root, the intersection point is, yet, the first approximation to the root. The intersection point splits the interval into two unequal subintervals. We need to determine in which interval the root lies. Here, we are visually able to determine that the root lies on the right side. A computer cannot make a visual determination, and it will require specific instructions to decide on how to narrow down the interval. We will check to see if fb times fx1 is greater, equal, or less than 0. If fb times fx is negative, the root is in the right interval. If fb times fx is positive, the root lies in the left interval. If fb times fx is 0, the midpoint is the root we are looking for. Since fb times fx1 is less than 0, the root lies on the right side. Now, we will calculate the intersection point x1. To do that, we obtain the equation of the line that passes through the endpoints, and then set it to 0. We then obtain the following as an approximation for the root. To generalize, we will make use of superscript notation to the following approximation. Before the next estimation, we update A1 with x1 and B1 with B0. We connect the endpoints of the new interval with a straight line, which intersects x-axis. We obtain the equation of the line that passes through the endpoints and set it to 0. The second estimate is the intersection point x2, which also splits the interval into two unequal subintervals. The value of fx2 is negative, and fx2 times fb1 is also negative, meaning that the root lies on the right side. Before the next estimation, we update A2 with x2 and B2 with B1. Although B's have not changed, we note that the interval shrinks and the lower endpoint of the interval approaches the root. We repeat this procedure again. That is, we connect the endpoints with a line and find the equation. And the intersection point x is the third estimate for the root, which is obtained as follows. The corresponding value of the function is negative, which leads to a negative value for fx3 times fb2. Then, we update the endpoints. The procedure of connecting the endpoints of an interval, finding the intersection point, and determining the subinterval with the root continue until the estimates converge within a specified tolerance. Note that in the course of bracketing, if the function fx is concave up, the right endpoint of the search interval is anchored while the left endpoint moves towards the root. But if fx is concave down, fx times fb is positive as shown in this figure. The left endpoint remains anchored while the right endpoint moves towards the root. Several stopping criteria can be applied either in terms of absolute or relative error or absolute value of the function for the current estimate. In the relative error criterion, a small number, the delta, may be added to the denominator, preferably in the order of machine epsilon, to ensure convergence in the case of zero or very small roots. It is prudent to use two criteria to ensure correct estimation in the case of very small or very large roots. The advantages and disadvantages of the method of false position are pretty much the same as those of the bisection method. For some functions, the method converges faster than the bisection method, but it can exhibit slow convergence in certain cases, particularly when the function is very flat near the root or when the initial interval is poorly chosen. The method may also fail to converge effectively if the interval bounds are not appropriately chosen. Consider the following nonlinear equation. Find its root, if it exists, in the interval between 1 to 2. The stopping criterion is based on the absolute value of the function being less than 10 to the power of minus 3. The endpoints of the interval are 1 and 2. We evaluate the function at x equals 1 and x equals 2. The intersection point is found as 1.123, 333. We evaluate the function for x1, which is found to be minus 3.03461. Now, to narrow down the search interval, we will check the sign of f2 times fx1. We observe that this product is negative, so we will discard the left interval. The left endpoint is updated as a1 equals 1.123, 333, while the right endpoint remains as 2. We already have f2 and fx1 from the prior step, so there is no need to recalculate these quantities. The current intercept becomes 1.214,023, and the function takes the value of minus 2.276876. Next, we check the sign of f2 times fx2, which is negative, meaning that the root is in the right interval. So we update the endpoints of the search interval. The left endpoint of the search interval is set to a2, while b2 remains as 2. When this procedure is continued, the root converges to 1.384, 306 after 17 bisections, with the convergence criterion based on the function value. The true root, accurate up to 9 decimal places, is computed to be 1.384,353,987. The estimate after 17 iterations is 1.384,306, which leads to the true absolute error of 4.78 times 10 to the power of minus 5, which is better than the desired tolerance of 10 to the power of minus 3. Note that this method resulted in more iterations than the bisection method because the root is close to where the sharp change occurs in the function f. That is all for now. See you next time with another topic. Bye.